shorter method. Does that make sense? But there's really not a wrong answer. I always try to do the dx first. Guys, what's the difference between the Riemann bars for the dx and dy areas? Do you remember? Yeah, the dx is like a tall Riemann sum bar, right? And the dy is like a wide, fat, right? Dy. Okay, so if I did a dx over here, okay, what you would do is you draw, little Riemann sum bars, dx's, okay, and you would get the area for each one of these. But do you guys see, I don't know if you can see it, the bars on this left side will have different areas from the bars on this right side. Can you guys see that? Because if you wanted the length or the height of this bar, okay, you see it would be y minus y, right? And this y here is a totally different function from this y here. You guys agree with that? So let me just draw this here. I'd actually like to do a dy on this one because I think it's a little bit easier. But I want to just go ahead and draw these two Riemann bars. So the height of this would be tangent x minus whatever the height of this is down here, or the y equals here, and that, you're right, that would be 0, okay? And that would be a dx. If I wanted one rectangle, it would be a dx. And if I wanted all the rectangles, it would be an integral of tangent x. Thank you. Okay. All right, if I want x here, this would go from x1 to x2. The x1 is pretty easy. It'd be 0, right? x2, a little bit more difficult, so I'll just put the x2 right there. All right. And if I wanted to add the red side Riemann bars, okay, do you see that this would be the integral of, okay, again, do you see that this would be y minus y, okay? The y on top here would be 2 minus x cubed, and the y on the bottom would be minus 0, right? This down here is y equals 0, and this would be a dx problem. Okay, times dx, this is the area of the red section. But I don't want just one area, I want all of them. So I put an integral there, and this would be from x2, I'll call this x2, to whatever this is. I'll call that x3. Is everybody good on if we did vertical Riemann sums with this? Okay, but I'm going to erase all this because I actually prefer to do a dy, just because that problem's a little bit, well, it's easier and it's harder. It's easier because it's only one integral. It's harder because it's a different type of thinking. Okay, so I'm going to go ahead and put a dy. Okay, so I'm going to put a whole bunch of dy's here, Riemann sum bars. Okay, and do you agree that if I pulled out a dy Riemann sum bar, that all of them would have the same formula for this region? Okay, so let's think about this. I need the area of this rectangle. So let me pull out one of these rectangles. I need the length right here. Okay, what is the length of this rectangle? Is it going to be a y minus y or an x minus x? X minus x, okay? And actually, make sure you understand, it's really a right minus left, right? If you do a left minus right, you're going to get a negative, okay? So you want to do right minus left or top minus bottom when you remember. All right, so this right here, I need an x minus x, okay? So what I have to do actually here is solve this for x. So right now, everything along this right side is y equals 2 minus x cubed. So to solve for x, do you see that this would be x cubed is equal to 2 minus y? So therefore, x is equal to what? The cube root of 2 minus y. Okay? On the left side, what are all these x's equal to? Okay, you agree the y is equal to tangent x, right? How do I isolate this x? How do I undo a tangent? An arctangent, right, or an inverse tangent. So what I'm going to do is I'm going to inverse tangent both sides. Okay, you do an arctangent both sides, which is the same thing as inverse tangent. If you inverse tangent a tangent, those are inverse functions, so the x falls out. So x is actually equal to, and I'll write arctan here, just so you understand that arctan is the exact same thing as tangent negative 1. They're interchangeable. Okay, so x is equal to arctan y. All right, so over here, okay, all my x's are equal to arctan y. All right, so what is the length of one of these bars? What is the length of it? X minus x, which is what? cube root of 2 minus y minus arctan y. Okay, so if I wanted the area of one of these boxes, the area of one of these boxes would be cube root of 2 minus y minus tangent negative 1y inverse y times d1, right? That's the area of one of the boxes. But I don't want just one box, but that is a formula for every box. I want a whole bunch of them, right? So what I do is I sum them all up, and that ends up being an integral, okay? This is a dy problem. So I go look at my region, okay? It should have been highlighted. So I go look at my region, which is highlighted, and I say, okay, what's the lowest y value on this region? What is it, guys? 0. What's the highest y value on this region? Ooh, how'd you get that? You might have, but you're ahead of us, okay? Exactly. So you need to go into your calculator and set your functions equal here. Okay, so let's go ahead and do that together. This is an exercise I want to make sure that you know how to do. They definitely, if they give you this type of free response, it's either going to be a fraction question where you need to know how to do fractions, or it's going to be a decimal where you need to be real comfortable with your calculator. All right, so we need the intersection of tangent x and 2 minus x cubed. So let's go into your equations. Okay, let's do this together, guys. It's a good exercise so you know how to use your calculator. All right, so on y equals, for y1, let's go ahead and put tangent x there. Okay. For y2, let's go ahead and put the other equation, 2 minus x cubed. Okay, and then I'm going to go ahead and graph this thing. Oh, wait. Sorry, you guys go ahead and graph it. Mine's set at a different thing. So when you graph it, did you get this funky thing? Did you guys get the same thing I got? Okay, does that trouble you at all? Because how can this be this? Or can it? Yeah, I just need to zoom it into this part here. Do you guys see that? So let's do a zoom box. Okay, you guys need to practice doing a zoom box, or zoom in will work also. I like the zoom box, but zoom in will work too. If I do a zoom box, I'll choose one, and then I pin my cursor at some corner of the box. So I'm going to pin my bottom left corner of the box, kind of at -1, -1. Okay, then hit enter. Enter pins that point. Okay, then I'm going to hit the up arrow, and I'm going to hit the right arrow. I'll hit the right arrow, and that's like kind of like an inset of a map. Okay, if I hit enter, it blows that part up. Okay, so that's what zoom box does. I think zoom in works too. I don't like zoom in as much because I can't control my picture as well, but either one should work. And this picture, I'm a little bit more comfortable. It looks more like this picture now. All right, what I want to do is find this point right here. So what I do is I do a second calc number 5, because that's intersect. Okay, I'm going to go to the left of the curve. I'm going to get a little bit closer to the point. Go to the left of the curve, hit enter, or left of the point. Sorry, left of the point, hit enter. Go to the right of the point, hit enter, and I'm telling my calculator, guess all those numbers between those 2 points that I gave you. When it says guess, I hit enter, and my calculator ends up with this intersection. Okay. Do you see that the y value that I want is 1.2657? You guys see that? The problem is you are not allowed to just write 1.2657. Like, you cannot round that when you put it into this integral. Okay, so what I'm going to do is I'm going to stow this y. Okay, and really for this problem, you don't have to stow the y. You could probably just use alpha y. But I'm going to stow the y because the real problem, when you did it on the free response, you had to stow it because you had this S region you had to find also, okay, for the real free response. So let's just practice stowing this number. So I'm going to stow the X and stow the Y into A and B, okay? So what I'm going to do is I'm going to second quit out of here, and that gives me back to my home screen. All right, you guys good so far? If you hit if you hit X and hit enter, that pulls back the X number. Your calculator has stowed that number as X. If you hit alpha Y, so alpha y and hit enter, I'll get that other number, 1.26265, okay? Now what I'm going to do is I'm going to change my x to a, okay? So x stow, bottom left here, alpha a, okay? And that changes that number. A is now 0.9021. If I put alpha A, okay, it's going to give me that 0.902 number. I'm going to change that Y to alpha B. So I'm going to hit alpha Y, so alpha 1, hit the stow button on the left, and change it to alpha B, okay? And now that changes, if I hit alpha B, it'll always give me that Y value, okay? And again, you didn't have to do it for this problem, but I want you guys to actually feel how you stow these numbers. And so what I would do on my paper, I would put this intersection as A comma B, okay? And then somewhere on my paper, I would say A is equal to 0.902 and B is equal to 1.266, okay? And I would put, you don't have to, I would put dots because these are actually rounded numbers, okay? And so what the AP reader is going to do is they're going to say, oh, okay, this point is AB, and right here, when I put A equals something dy, what number do I want up here? Do I want the A number or the B number? What number for this limit up here? Yeah, the B. So I'll just put B there, and that will be counted right, okay, for the AP reader. All right, and I don't have to put that whole number there. I can just put B. All right, so I'm going to enter this into the calculator. What's nice about entering this into the calculator is I can actually just enter B into the calculator, just like this. So let's enter this into the calculator. Let me do a math 9. Okay, this will go from 0 to B, so alpha B. Okay, put the integrand right here. The cube root is a math function, so you can do math number 4. That's a cube root function. And that's going to be 2 minus. Now, you could do 2 minus y. It wouldn't hurt. But you can also just put x, okay? Because your calculator is just using some variable. It doesn't matter if the variable is x or y or b or g, okay? I'm just going to use x minus the inverse tangent. So that second tangent, again, I'm using x. So I'm going to put an x instead of a y. You could use y. You just have to push an extra alpha if you want to use y. And then I'm going to use x here, okay? Then I pray. And I hit enter, and that is the volume, that is the area for this region, 7.729. That is the area. Okay, can you do this on your own? Feel comfortable with it? Okay, go ahead and pass up your warm-ups, and let's look at your homework. There's 14. All right, your picture should look something like this, okay? And this is your shaded region. Your shaded region is right here. Right here. Okay. These are cross sections perpendicular to the x-axis. So guys, already I know my formula. You guys good with that? Already, this is the formula. You can look at your formula, your quotable, but this is your formula. Okay. I just need the area of cross sections perpendicular to the x-axis. So this is a dx problem. I'm going to pull out one of these slivers, okay? These slivers have semicircular cross sections. So one of these slivers, okay, this is the diameter of the cross section of the circle, but this right here, this diameter is this length right here. Everybody good with that? I just pulled out one of those pieces. Okay, let's just pull it out. Guys, if I pull it out, what is the length of this piece? Okay, is it y minus y or is it x minus x? Do you see it? Y minus y, everybody good with that? Okay, so let me get my y up here. The y up here is y equals square root of x. And that y down here is y equals x. So this diameter is square root of x minus x. What's the area of this semicircle? Because that's the area I'm going to plug in right there. The area formula is pi d squared over 8. That's going to be pi square root of x minus x squared over 8. And then I just plug this area right into this formula. So volume equals, I'm going to pull out the pi over 8 just to make it a little bit simpler looking. And this will be square root of x minus x squared dx. Okay, and that's your formula. I need to find the limits, though, of my x. So if you go to the picture, what's the smallest x value? 0. That's pretty easy. But what's the largest x value? I need to find this intersection here. The intersection is where y equals square root of x intersects with y equals x. You just set them equal, so that means square root of x is equal to x. Is that right? Y equals square root of x. Yeah. So then this means square of x, well, let me just square both sides. So that's x equals x squared. So that means 0 equals x squared minus x. I need to factor them somehow. So x minus 1. So x is equal to 0 or x is equal to 1. So this must be 0 something, and this one must be 1 something. I could find the y, but do you see I don't need it? If I could find it, I would just plug it back in. Oh, it'd be the same. It'd be 0, 0, and 1, 1. So this would just be 1. Okay, you guys good with that? And are you guys okay if I don't solve it? I'm going to let you guys solve it. Yeah, Mary.
I just see
C15, yes. So there's 15. You good with that? That's the setup. Some people highlighted this whole region, but you're only supposed to highlight this top region, just FYI, because it says x-axis is one of your boundaries.
Oh, okay.
Does that make sense? Okay. Okay, you guys good? All right, let's move on then. Go ahead and open your folder to the third part. We're going to look at volume of a disc. Really, volume of an orange, AKA. Let's look at volume of an orange. So I've got this orange here. What I'm going to do is I'm going to slice it. We sliced it in first period, and we didn't do a very good job. But just FYI, it's okay. If I wanted the volume of orange, one way I could do it is I could slice it. Okay, and think about this. I could slice it and then pull out a slice. Right? I could pull out a slice. Okay, because there's an infinite number of slices here. I could pull out a slice, get the volume of one slice, and then add all the volumes together. Do you agree with that? Right? The volume of one slice and add them all together, because they're all going to look like this. See, every time I pull one out, it'll look like this. See, they're all going to look like this. I'll pull out another one. Don't look. Okay, look. See, it still looks like that. Right? Okay. So that's how I'm going to do it with calculus. Okay. So I'm going to cut this thing into slices. Okay. Infinitesimal slices, like super thin slices. Okay. But wherever I put the slice, okay, when I pull that slice out, it's going to look like a circle. And this doesn't have to be an orange. It could be a cucumber, right? If you took a cucumber and sliced it, every slice would look like a circle, okay? Unless you had like a weird cucumber, okay? And the volume of one of these slices, okay, would be this area times the infinitesimal thickness, which would be a dx thickness, okay? And so if I wanted the volume of one of these slices, do you see it would just be ADX, right? It'd just be ADX, okay? But if I wanted to add every single one of them together, if I wanted to sum all of them up, okay, do you agree that that would be the integral of ADX, which is the same formula we had before, the exact same formula with cross-sectional volumes, okay? The only thing is now the area is not a triangle formula. What's the area going to be? A circle formula. What's the area for a circle? Pi r squared. So your new formula, guys, is going to be B equals pi r squared dx. That is your new formula today, okay? And what we're going to do today is see if this makes sense. We'll put this onto some sort of graph, okay? And I'll call this the function. I'll say this is the function f of x, okay? This is a function f of x. It's some function, okay? And it turns out that if I take this region right here, if I, let me see if I can highlight this region. If I highlighted this region right here, oops. Okay, when you highlight yellow on orange, it doesn't do anything. Okay, so if I highlight this region right here, and I rotated it about the x-axis, that would also be the volume of the orange. You kind of agree on that? Okay, and so, but if you highlight this and you rotate it, it turns out that it's the exact same thing as if you took slices out and added all the slices together. It's the exact same thing. So what we're going to do today is if we could just find the radius of the figures that we rotate about an axis, okay, we could stick it into this formula and we can find the volume of all of these, we call them discs, okay, because we rotate these things. We rotate these discs, okay. The hard part, well, it's not really super hard, but it's identifying the radius, okay. So do you see that the radius is always, it's always from the axis that you rotate through the region to the furthest point on the region. Do you see that? And that's always the radius, okay? So let's look at some problems, and this will make a little bit more sense to you, hopefully. Go to your third page. Please put dx on the left, top left, and dy on the top right. And I only use the bottom portion of the paper, but remember, you're free to use the top whole white section too, okay? In the first example, this is going to be the dx side, okay? Oh, actually, go ahead and write these formulas first, okay? On the left side, your formula is going to be pi integral of pi r squared dx, okay? That's your formula. The pi is a scalar, so we pull it out. You could pull it out or leave it in, it doesn't matter. I think it's easier if you pull it out, okay? So pi r squared dx from x1 to x2. On the right side, in a dy problem, your formula is going to be the same, pi r squared, but now it's dy. And of course, it's dy. It's going to be from y1 to y2, okay? An extra tidbit is on the left side, your r is always going to be top minus bottom. I actually don't memorize it, but if you want to, you can. Okay, and on the right side, your r is always going to be right minus left. Okay, the other thing that's really important to know, and please make a note of this, dx's are used when you rotate around any horizontal line. If you rotate around a horizontal line, like an x-axis, or any line that's y equals a number, okay, that's always going to be a dx problem. Because y equals a number is always a horizontal line. Okay, the dy side, please make a note of this, is used when you rotate about any vertical axis. Okay, and that's like the y-axis or any x equals number. Okay, because that's going to be a vertical line. Okay, and the final thing that you need to make a note of is what r is. R is always, okay, defined as from the axis of rotation through the region to the furthest point on the region. Okay, from the axis of rotation through the region to the furthest point on the region. Okay, and that is really nice today, but tomorrow this will really help you out. Okay, this R. All right, the definition of this R. Let's go ahead and get started. This is your first problem here, I think, right here. Okay, go ahead and draw your picture, and I'm going to pull out all this extra stuff on the picture. So go ahead and draw your picture. And shade in the region. So this region is defined by y equals 2x, y equals 0, and x equals 3. It turns out it's a triangle. And we're going to take this triangle and we're going to rotate it about the x-axis. So when we rotate this about the x-axis, what kind of volume is it going to look like? It's going to be a cone. So we're going to find the volume of this cone, okay? If I took slivers of this and pulled out a sliver, okay, what shape would the cross-section be? A circle. And that's why we're going to use the v equals pi r squared dx formula, okay? So what we're going to do is we'll rotate this triangle about the x-axis, and the formula we're going to use is volume is equal to pi integral r squared dx. Now, why is it a dx problem? Because we're rotating around about a horizontal line. Okay, that's why we're doing that. All right, why we're using dx, okay? Now, all you do is you plug into this formula. You find your r. Remember what we said r is? R is from the axis of rotation. So I would come up here and I'd put a dot on the axis of rotation. Because let me put a spin on this x-axis to make sure we understand. We're going to spin around this x-axis. So from the x-axis, from the axis of rotation through the region to the furthest point on the region, label that as your r. Once you draw your r, forget everything you said. Forget that whole axis of rotation stuff. Forget it, because it's going to confuse you. All you do is you grab your r, pull it out, and say, how do I find this r? Is it y minus y, or is it x minus x? What is it, guys? Y minus y. So get the y on top, get the y on bottom, okay, and find the length of your r. What is r equal to, guys? 2x minus 0, okay? Then what you do is you just plug that number right into this r, right? Plug this 2x right into this r squared. So what I get is volume is equal to pi 4x squared dx, okay? This is a dx problem. So what I do is I go look at my shaded region, find the lowest x value. What's my smallest x value? 0. And this intersecting point is 3, 6. What's my highest x value? 3. And so there's my integral, okay? If I had to integrate it, this would be 4x cubed over 3 from 0 to 3, actually times pi from 0 to 3, okay? So this would be equal to, first, this is pi. First, you plug in the 3, okay? Then you plug in the 0, then you slap a minus sign in the middle, okay? And this would be down here 1, this would be 9. So my answer is going to be 36 pi, okay? And that's the volume of this cone that would be formed if I rotated this shape, this region about the x-axis. Any questions on that? All right, let's do another one, and you'll get the hang of these. All right, on the bottom left, so we're still on the dx side, okay? On the bottom left, go ahead and draw your region and highlight your region. Look at the bottom left, we're still on dx. And we've got this triangle, and what we're going to do now is we're going to rotate this triangle, or this region, about the horizontal line y equals x now, okay? What volume are we going to get when we rotate this around? Still the same, okay? Actually, because I only have this thing, all your volumes are cones, but it won't be so for your homework, all right? Okay, so right here, we're going to find the volume of this cone when this region is rotated around. Make sure, I'm going to put a spin here, make sure you understand, we're rotating about this axis right here. The y equals 6, okay? So the formula is volume is equal to pi integral r squared dx. It's a dx because we're rotating about a horizontal line, all right? We don't get to choose. When you're doing area, you can choose, okay? When you're doing volume, the problem defines if it's a dx or a dy. All right, let's find our r. Remember, r is from the axis of rotation. Put a dot on the axis of rotation. Through the region to the furthest point on the region, and that's my capital R. Okay, so guys, if that's my R, okay, what is the length of R? Let's pull it out. Okay, forget the whole thing about the axis of rotation. You've already drawn your R. Pull it out. Is it a y minus y or an x minus x? Y minus y. Well, the top y is what? Y equals 6. The bottom y is y equals 2x, I believe. So what's your R? 6 minus 2x. Then all you do is plug it into the formula. So what we have is v is equal to pi integral quantity 6 minus 2x squared dx. All right, let's go ahead and get these limits. This is a dx problem. So I go to my highlighted region. Let me put this, I think this was 3, 6. Okay, what is my lowest x value? 0. What is my highest x value? 3. And I'll let you guys integrate that on your own. Okay? Any questions about how to set this up? Okay, let's go to the right side. So now, guys, we're on the top right. Okay. This problem right here. Ooh, top right. Okay, this problem right here. Okay, go ahead and draw your region. Highlight your region. I've got it up here. And now we're going to rotate this region about the y-axis. So I'm going to put a spin on the y-axis. Okay. How does this formula change now for volume if I'm rotating about the y-axis? Now this is pi r squared dy. That's pretty much it. It's really the same formula. It's really a dy, okay? But if I spin this around and I grab cross sections, I pull out a cross section, it's a circle, right? So your area here was pi r squared instead of, all those other formulas you were doing yesterday. Okay, it's actually the same formula. Okay, so pi r squared. All right, let's find my r. Okay, r, remember, is from the axis of rotation. So now I'm rotating about the y-axis. So let me put a dot right on the y-axis. From the axis of rotation, go perpendicular to it, go through the region to the furthest point on the region, and there is my capital R. Okay? And guys, these capital R's are like Riemann sum bars. So doesn't it make sense that this is a dy problem, right? Because your capital R is like a Riemann sum problem. Okay, let me pull this R out. Forget the whole thing about the axis of rotation. I'm going to pull this R out. Okay, guys, the length of this R, is it y minus y or x minus x? It's x minus x. Okay, so now go back to this thing and figure out what is the x equals to all on this side. What is it? It's no longer y equals 2x. It's x equals what? Y over 2. Okay. Over here, what is the x equals all along this side? It's x equals 0. So what is the length of my r? It's going to be x minus x, which is y over 2 minus 0. Is everybody good with that? Okay, so all I do now is actually just plug that in. So the volume is equal to pi integral the square of r, so it's r squared over 4 dy. If this is a dy problem, I go back to my region. I say, what's the lowest y value on this highlighted region? What is it, guys? 0. What's the highest y value on this highlighted region? 6. And bam, this is actually a y. So bam, there's my formula. Do you guys see how easy this is? If you take it one step at a time, don't skip steps. Take it one step at a time. All right. And then finally, our last problem right here. Let me see if this one is. Yeah, our last problem right here. Go ahead and, time's up. Go ahead and draw this region right here. And we're going to rotate this thing about x equals 3. That's what the problem says. Rotate this problem about x equals 3. Okay, so what is this going to look like? See if you can imagine it 3D. What's this thing going to look like when I rotate it? Oh, why? It's a cone. Okay, so this is also a cone. Of course, you could do it with geometry, but why would you want to do that when you know calculus? Okay, so what we're going to do is we're going to write the formula. Okay, again, when we rotate this cone, when we rotate this figure to cone, if I took cross sections and I took a sliver out, it would be a circle. Okay, and that's why this formula for volume is actually pi r squared. Okay, but guys, we're rotating about a vertical line, so that's why it's the dy formula. If we're rotating around a horizontal line, it would be a dx formula. Okay, all you have to do is define your r. Guys, r starts from where, guys? What does r start from? The axis of rotation. Put a dot on your axis of rotation. Okay, from the axis of rotation through the region to the furthest point on the region, label your r. Okay, remember your r is like little Riemann sum bars, so it makes a lot of sense that this would be a dy problem. Check it. If you made a horizontal r, make sure that that's a dy problem. Okay, and then let's go ahead and define my r. Okay, I'm going to take this r. Forget the whole thing about the axis of rotation. That confuses students after you found your r. You take your r and say, hey, is this an x minus x problem or a y minus y problem? What is it, guys? X minus x. So what's the x on this right side? X equals 3. What's the x on the left side? X equals y over 2. So what's the length of this r? 3 minus y over 2. And then, guys, you just put it right into the formula. 3 minus y over 2 squared dy. Don't forget the pi. Actually, that's what I forget. If you forget the pi on your homework, on your test, you just get a -1. Okay, as long as it was set up right. And so, guys, this is a dy problem. So go look at my region. What's my lowest y value? 0. What's my highest y value? 6. And there is your formula. How are you feeling? It's not too bad, right? Take it methodically. Now, we didn't solve these problems, so I just want to take you guys to take note. The biggest mistake students make is this pi, okay? They either forget the pi, or instead of pi, they use 3.14159. You guys are not allowed to use 3.14159 because that's a rounding error. Does that make sense? If you use pi, if you actually multiply it out, which I don't, I usually just put pi as the answer, which is totally fine. But if you multiply it out, use your pi button. Is everybody good with that? You have a pi button on your calculator, and that doesn't round, okay, or goes pretty far, okay? If you do have any decimals, make sure you go 3 places, and then you won't get it counted wrong on your test, okay? Any questions, guys? You guys are good? Okay, we're finished early. We have 2 minutes. I can set up a homework question if anybody would like me to set up a homework question from today or yesterday. If anybody's working on stuff and they're not sure about what to do. You guys are good. I haven't really looked at the homework. It's front and back. You can use your calculator, so if you need it to graph the equations, feel free to do that. I would use your calculator when you need to. If the problem gets too difficult, please feel free to use your calculator. Otherwise, see if you can do it by hand, because sometimes you will have to do it by hand. Your test again is all calculators, so most of you guys will be fine, except when you draw the sideways parabola. Okay, you guys seem like you're either asleep or you're fine, so